All right, we have some more time at hand, and let's continue with our parser. So we have our program so far that it can parse. Oh yeah, of course, because we changed the script to foo. So if we change that back to void and run it again, it should actually be a type we recognize. And yeah, now we're failing at the parameter list, and that's the end of the parameter list. So let's continue with our parser class then, because we have now a parser that will parse a function definition, and if not, output errors for like all the unknown identifiers that it encounters. Because we don't match this void as a new function start, by the way, even though it is a type, because it doesn't have an opening bracket. In fact, none of these have. And of course, printf doesn't have a type before it. So even though it has an opening bracket, you know, like it's not a complete sequence. It doesn't, like we need type, name, opening bracket. That's all we parse right now. And this one doesn't have a type. And this one is a type and a name, but then followed by an equal sign. So won't match either. And that's fine. That's how we wrote this script. So now we want to parse the function. So what do we do here? Oh, by the way, I realize there is one thing that we can do to make this a little nicer, and that is to make backtracking easier, because we know like the entire function definition is invalid once we hit a point where we want to backtrack. So what we can do is we can say vector token iterator parse start equals current token. Sorry, I bumped the microphone there. I hope that wasn't audible. And now we can just, instead of having to remember how many tokens we failed with here, we can of course just go back to parse start. So that's a little nicer. Okay, so now we have a possible operator has value. So we now know now it's an opening bracket. And now we have to, if we look at the code, wait, I think I can show a split view, can't I? Can't I split this here somewhere? I guess not. Okay. Maybe here. Here. Okay, that was the wrong split, but basically it's the right idea. So split vertically is what they call it. The problem is always split it with a horizontal or vertical line, or split the whole box so the vertical edges, you know, like it's anyway. So we have our code that we want to parse here, and if you look here, like right now we only have void. Let's say int argc, and let's just make it we don't have pointers yet, so I'll just call it car argv for now. You know, like it's the standard names of like the parameters that we have in a main function in C. That's why I'm choosing it, because you should be familiar with it. But of course we can't parse the whole, you know, character array yet. So this is just a char for now, but that's fine. So now we have a list of parameters. And so now what we want to do is we want to see, are there any parameters at all? And we can tell that by seeing if the next character is a closing bracket, because that indicates that it's just an empty list. Or rather, if we wanted to be really strict about C, like you usually say void. So those are both cases we have to cover. So let's say if expect operator closing bracket not null opt. We don't really care about the result in this case. Or expect identifier void. We should probably, no wait, we can just cover this. We don't even have to special case void, never mind. So if it closes here, just because, people are used to C++, and if you're implementing your own language, you'll probably support that. Because in C, the just having empty brackets is old Kernighan and Ritchie style. So before it was standardized, and it means that the parameter list follows the closing bracket, which, I don't want to implement here. I just want some standard C. So I'll just say if it's that empty case, then we can just parse function body. And that's a function we'll have to create. Yes. Okay, so we'll do that later. So where were we? Expect function definition, parse function body. I'm doing this in a separate function because one, you might do other parsing things that might look like a function body as well or whatever. And then maybe you can use this. You could use this for a loop as well, I guess. Although then you'd have to rename it, I guess, because it's not a good name, of course. But also because in the else case, we'll have to do the same thing. So else. And now we just loop. So while, let's say bool more parameters equals true. We know it's not an empty list, so there has to be something in there. So while more parameters, and now we do optional type, possible type equals expect type. All right. So far, not a problem. If not, so and now we of course have to detect, like, what if it's, let's not go with more parameters, let's go, right, we don't even need this case, I think. So let's just put this down here, get rid of this again, and now instead say while expect operator closing bracket equals null opt. So that means if it, this is only the start. We then parse the entire int name comma part. So we don't really need to continue going here. No, not continue going. I mean, so if we don't find a closing, no, actually, let's just say while true and do this afterwards. Because we need to cover two cases here. If expect operator not null opt and expect operator, or expect operator. No, actually that should be an error. Okay, so I'm still building the kind of the structure of what I want to do. So one thing we have to do is we have to exit when it's the end of the parameter list, of course. No, actually, let's put that in there after all. While it is null opt, so we keep going. And now at the end, if wait, I think I've copied that. Yeah, if expect operator comma equals null opt. So if we don't have a comma following the whole parameter that we've parsed, we're only parsing the type right now, but we'll do that in a second. So there's more to come here. But then, of course, we want the list to be comma separated, so we'll check. And if there is no comma, then that probably means there's a closing bracket. No, wait, we can't really. We still have to check for that one as well. If it's not a comma, and it's not a closing bracket, then what we should do is throw an error. Or closing to indicate end of argument list. Or is it parameter list? I'm always forgetting, like parameter is like one of them is what you put into the function. So basically, I think this is an argument and these are parameters. So basically, when you're calling, the stuff that you put in is an argument. And the mailboxes in which parameters arrive are parameters, something like that. It's used interchangeable by lots of people and by me as well, so I guess that's why. Anyway, so we are here. Okay, we have covered the error case. And now we need to say if possible type equals null opt, so we have no type. Then we throw another runtime error. And we say expected a type at start of argument list. I don't care if it's parameters or arguments. And now the other thing is that, of course, the parameter name is, or argument name is optional. So optional token possible variable name. And by the way, for cases like this, you could possibly make an expect type function that just returns an optional and another one that throws on itself to make the code a little easier and to not scatter it with all the error handling functions. I kind of like to put the error handling here because then I can tell it what I was trying to parse and give hints like, it won't just say expected comma here, deal with it yourself, but rather I can say, this is a parameter list, or hey, a comma or a closing bracket would have been valid here. You could, of course, also do an expect operators function that takes a list of possible operators and then, but you can kind of combine it. You could also just pass in a parameter that provides additional information, like, that you say expected, and then, provide a string. And then I would just say expect operator, comma, closing bracket, comma, while parsing argument list or whatever. Okay, variable name, and that's expect identifier. And we accept any identifier here, really. All right, so now we have this, and now we need a new data structure to describe our function. And what we should probably do for that is we should create that new, call it function definition. Pragma once, namespace, simple parser. Using namespace standard. And now, right now, this will not be that complex. So we need a parameter definition, and that should contain a string, which is parameter name, and a type, parameter type. And of course, now we need here a string function name. We can probably just make this short and say mname and mtype. Same here, mname, and then vector parameter definition parameters. Kind of like that. We also need to include vector, of course, for this to compile. And now it wants the type from parser.h, and that's probably a good opportunity to pull that one out into its own header, because otherwise we'll just end up with this circular dependency. New C++ class type. All right, and now we get rid of this stuff that I copied because we only need the type. Let's see we're using vector, we're not using map, we're not using optional. I don't think we're using tokenizer either. Oh, but we forgot to include vector here. I guess that implicitly got inherited. Okay, so let's go back in parser and actually include vector just to be safe, in case tokenizer ever changes. And of course, we need to include type now. And now in function definition, we also need to include type. All right, so we have the parameter definition, we have the type, good. And now we go, like we could do this a little cleaner, you know, we could probably add functions, you know, accessor functions for the instance variables for the name, and, you know, add an add parameter method that, you know, but we'll just end up calling parameters pushback right now. That's, you know, fine for this one. So I'm taking a few small shortcuts here. All right, so now we have we need a function definition here. And we need to include that as well, of course. So what you need to do, of course, if you parse a program is you need to keep the stuff that you parse somewhere. So in this case, I think we'll use a map as well. I'm sorry, I keep bumping the microphone. I hope that that isn't audible on stream, actually. Okay. So func, and now func.name equals possible name text. All right. And now parameter definition param name equals type equals possible type name, and if so, in this case, you know, I don't need I don't actually need to be able. Oh, I should actually be using has value, shouldn't I? Not equals null opt. Because who knows what that does. Wait, if not has value and closing bracket not has value. Possible type, and here again not has value. And so if the variable name has then param.name equals possible variable name text. All right. And now func.parameters pushback param. So what we're doing now is we're looping over the argument list, grabbing the type and the optional name of the argument, and creating a parameter definition that contains this information. Since there are no empty identifiers, I just don't set the string and it ends up empty. I guess, like, technically you could argue that this should be an optional type to make it clear when we have one and when we don't have one. I think that's, being a little excessive, because then you have two cases technically. You could have an empty string and you could have it optional. So in that case, I would probably just go into parameter definition and say empty string means no name given. I don't know, that should be enough, right? Oh, and now, of course, what we want here is we want a debug print function here as well, like we've had on the other object, and we make that wait, let's just say generate definition. All right. Include IO stream, so we can actually print something, and then say name, opening bracket, actually, since we want to print this in a block, we can just use \n here. We only need the endl at the end. Cout all right. Oh, I forgot the using namespace standard. And now for what is it? Parameter definition param in parameters param debug print. Okay, so now we print each of these. Param doesn't have one yet, so we'll create that one. And so that's been added to the parameter definition as well. And now for the parameter, we say cout type name space type just name, and say endl here, I guess. Line end. Okay, so what we're doing here is basically just printing out the hierarchy. So we're printing out the function name and the parameters are listed as type and name. So it looks pretty similar to how it would here, just without the commas and in multiple lines. And now we can go to our parser. I think the parser doesn't have a debug print yet. No. So we'll need that as well. All right, and that's a const function as always. Should probably have done that, because it should not modify anything. So we might as well tell the compiler about it. Okay, so now we have a debug print. And in that one, we just say for function definition func in functions func debug print for now. That should be fine. And now in our main function, so we know what we did, is we call parser debug print. And while we're at it, we know that the tokens are working now. So let's comment those out. And we really know our file contents as well, so let's comment those out as well. We don't need to print them right now. Oh, and I didn't stick to the naming convention. Refactor rename. All right, debug print, parser is lowercase. All right, so let's run this and see what happens. We typed something wrong. Oh, function definition. Oh, that's a map, of course. So this is func pair and func pair second, of course. Let's just make this auto. And I think dot second, yes. All right, now it should run, shouldn't it? Or did I do something silly like that? Okay. Let's see how far we get. Unknown identifier int and argc. So something isn't quite right there yet. Okay, let's just go back to expect function definition. We know we can get to this point because we had it print before. Oh, wait, I need to start the debugger, of course, not just run it. All right. So let's step through here. Oh, of course, I did this one wrong. So abort has been called. Why are you unhappy? Oh, it's probably just the breakpoint. I don't know. No, maybe it just stopped at the break. Okay, not. Oh, we don't have a closing bracket. That seems fine. Possible type. If we have no type, no, but we have a type. And now, so we're basically here in the parser now. So if we see possible type value, is actually void. Oh wait, that's the wrong one. Ooh, we have two variables named possible type. That's not a good choice. So rename this one possible param type. Okay. Oh, and this one, no, it's returning true, so it's fine. Okay, just to be safe, let's run this in the debugger again. Otherwise it might show us wrong offsets or something if it hasn't rebuilt it. Okay. It's not a closing bracket, it's an int. We have the type and the possible param type is signed int. That's fine. That's what we called it. Optional token possible variable name. It's just any identifier. So possible variable name is argc, which is right. So now parameter definition, set its type to that name. And if the name has a value, set its name to that as well. So param is argc of type signed int. Oh, we didn't set the built-in type yet. We should probably do that in the array. I think I overlooked that. But anyway, so now we push that back in func. So if we look inside func now, it has the name main and it has one parameter, and that is argc of type signed int. So that's correct. Now, if not comma or not already has value, I hope. So let's see, did we skip the comma now? In this current token is what? Identifier. That 0 makes me a little worried. But that could just be the debugger showing something weird. Let's see, where are we now? Doesn't have a value, and now possible param type, expect type. What is possible param type? Signed char int 8. No, that's right. Oh, wait. This already consumes the closing bracket. So we actually could have left it. Okay, so let's say if has value, then break, because we're done here. Otherwise, if it doesn't have a comma, then throw an error. So at the least, that should get us further. Yeah. Now you see, unknown identifier, the first one is the opening bracket. So it's parsed the entire thing. So now why isn't it actually printing our debug print? Wait, wrong one. Debugger again. continue debug print. Now we step into that. We don't have any functions. Size 0, yeah. Did I forget to push the function in the parser? Of course, I only put the parameters in the function, didn't I? Let's see. Yeah, okay. So here, functions push back. Func. Okay, and of course, what we need to do is we need to pull. No, func is in the right spot, I think. Yeah. Why is this red? Rename reference. What is it saying? Oh, it's a standard map, of course. So what we want to do is functions func.name. That should work now, right? Yes. And now you see here at the bottom it prints. We have a function main. It takes assigned inc argc and assigned char argv. So we have an object that again contains objects for its arguments. And that basically is how you would, parse any any programming language. You build a tree like that of all the commands and things in your program. And then, you can just, in our case, we just print out that tree, but the same way you could just recursively evaluate your tree data structure. So let's continue that. We have parse function body, right? So we say if not expect. So we need the curly bracket first. Has value. Then throw, oops, runtime error. Expected curly bracket for function definition. And now, of course, this is a case where you could also backtrack and fail. Actually, we should probably do that. Yeah, return false. Otherwise, return true. Expect operator. Closing curly. And again, just make sure that the closing one is there, otherwise something is wrong with the code. All right. By the way, one of the things I usually do, which I won't do for brevity, is usually you don't just use runtime error. Usually I define my own exception subclass, usually a subclass of runtime error or something, that's fine. And put in that member variables for, start offset, end offset, and line number, so I can report the error with more precision, and that, like in this case, I would just get unbalanced closing bracket. I wouldn't have no idea where in the program it is. Though I guess, yeah, let's leave it like that. Because, you know, otherwise now I would have to cope with the case of the script ends here. So I'd have to say, okay, if there is a next token, give me its offset. Or rather, give me the previous token's offset, I guess. But anyway. All right, so and now here we need to parse statements. So parse one statement, something like that. Oh, come on. Create new function. Yes, that's fine. And that's basically the recursive part. You know, you just take the parts of your program and go, okay, what are these? These are types, so we have a parse type method. Then this is a function, so we have a parse function method, of course, that calls parse type. Then we parse a name or something. Then we have a parameter list that could be a separate function as well. We're just doing that here now, but like as soon as we did a function declaration, you know, which ends with a semicolon, then of course we would want the parameter list parsing code to be shared. And then every function has a body, and you know, like a function may have additional qualifiers in between here. I don't think that's a C thing. I think that's a C++ thing. Well, but still, like for example, GCC lets you put attributes there, so it's not that unheard of, you know. But like in C++, of course, you have const or something. So you might want to parse that as well. But anyway, then you say, okay, and what are these things? These are statements. So you parse a statement, and then you write a function for parsing a statement. And so then you say, okay, if a statement starts with a type, so optional type, possible type equals expect type. Oh, and we should probably remember the current offset. So vector token iterator. I should probably type def something for that as well. Start token equals current token. If not possible type as value, then return. And what else do we do? Well, we should, I think in this case it's not necessary because expect type wouldn't set it, but just to be consistent. Otherwise, when we move around code, suddenly it won't be right anymore. Parse one statement, and now optional token possible variable name equals expect identifier. Any identifier is fine again in this case. We haven't really done anything that expects identifiers in particular. Like we haven't implemented a for statement that always starts with the word for. So we actually haven't used expect identifier with a parameter yet. But all right. And so now if not token has value, then reset it. In this case, it's important because we might have already consumed the type. And return. Oh, and we should probably give that a type. So the thing is, since you're building a tree, we should probably return something from all of these functions. So in this case, I don't know, we might invent a class named statement. Create a new C++ class, statement, yes. Namespace, sample parser. Once. So we don't really have anything, but I guess we'll make that a virtual class. Where's the tilde key on this keyboard? Here. That's weird. Oh, it's up here. Okay, that's, I guess I have the wrong keyword layout set. Happens, okay. Virtual. Wait, I think I can say default here, because I'm not actually implementing anything, but we will have subclasses, so it needs to be virtual. And now we say a variable declaration statement is a statement. No, we can't really. If we're doing that with optional, we don't want to use subclasses. So you could do it with subclasses, but right now we'll just rough it and say, okay, string name using namespace standard and include string type mtype, and then let's see, vector statement for parameters if we have any, and then we'll just reuse that. Okay. And we should include a vector as well. All right, so this is just, we want this data printed somehow. Right. Namespace. Again, our usual dance. I need IO stream. And now we can say cout name type name, just so we print it out somehow. And then for what do we have? Right, these are all just statements. parameters. So, you know, I'm just gonna shoehorn this one in a custom statement for now, and then just say, you know, that they're just recursive, really. But let's see. I think we'll add a bool is a variable. Oh no, let's add a statement type. Statement kind, maybe, because type is something else. It's a bit inconsistent now with the token type, but never mind. And now we say variable declaration, comma, function call. So basically we're kind of simulating an object-oriented hierarchy or something here. That's why you could do it with a subclass better. But right now I just want to show what you can do in a parser, so I'm kind of going to take this shortcut. All right, where are we? Somewhere in the parser. And here we have parse one statement. Possible variable name. And now we say what do we say here? The variable name. We should really, like, this is not just, like, right now we're only parsing the variable definition. Of course, we need to handle the second case as well. But let's see. Statement, return statement kind equals variable declaration, and statement name equals possible variable name text, and statement type equals possible type. All right. So we have unpacked the type here. And let's make this more readable. Dot value. All right, so we have this, and we can return this. So it will fail as soon as it hits the equal sign, of course, because the next thing we'll have to do is cover that case, but we need to do a lot more work because we also need to parse a grab a literal in that case. So let's just run that for now. Oh, and we need to update change type. Yes. That should be correct now. Oh, it didn't correctly do it. Probably because it doesn't know statement at this spot. All right. It's always nice to have an editor that is as helpful as this one, but okay. Parse function body. Oh, we have the same issue with parse function body, I guess. What does parse function body do anyway, or return anyway? Oh, I changed it to use a bool. Okay. Both functions to bool. Okay. Okay. Why was it unhappy? Oh, right, yeah. I think we shouldn't. Come on. We can't check that yet because we already, fail here. So at this point, we give control back to the function body stuff and it will complain about this. All right, and let's see what it did now. It didn't get to the double. Do we not have the type double? Or did I do that wrong? Yeah, it didn't do double yet. Double, double. Okay, and let's see, I think this one, name and type. No, it should work. Read why it had the wrong type earlier. But okay, anyway, this should at least work. Yeah, and now let's, now you see we're only failing at the equals sign. But we're not actually printing what we parsed yet. But statement has a debug print, of course, but we're not printing or appending the statements yet. Okay, so far it seems to sort of work. That's good. And parse function body should really give a vector. I guess we need to give an optional, because an empty list is valid, a vector of statement. Okay. Okay, let's see if it did that one right. Okay, almost. We have statement included, so that should be fine. Okay, and now we go to, of course, here we return null opt. And here we do a vector statement. And so we should really be looping here. We're not doing that yet. Push back. We'll do that in a moment when we have more of our statement actually parsing. Because if we try to parse for next statement right now, we just get an error messages that this is not a semicolon, because we're not parsing the entire construct yet. So of course that makes no sense. We return the statements here. And now who calls parse function body? call that here. And so vector statement. Oh wait, this is the optional. So if, and that's the nice thing, because we're building it on the stack in the variable func first. This means that it will leave nothing behind until we actually add it to the mfunctions array, in our compiled program. And so that means we can backtrack here if we want to. If statements, okay, if we don't have a value here, I have to be careful. What do we need to do now? So we need to, if this is not correct, then we need to return, we set current token to parse start, because we're bailing out here. And we return false. We could probably even, instead of returning true or false here, actually have this function return an optional function definition. We might change it to that later. Let's leave it like that for now. What are you unhappy about? Oh, that's still an optional. Where is that? Okay, yeah, we need to, okay, never mind. Optional statement equals parse one statement, and then if, whoops, no, I copied it. If statement has value, then push it back. All right, that should work now. It's all those small typos you make. Yeah, I think it ran through. Oh, and we haven't added the statements to the function. Of course, we need to do that. And I think our function doesn't know about statements yet. So, function definition, yeah. Vector statement, statements. All right. And now we go back. Where are you? Parser CPP. And say func dot, oops, statements equals statements. Oh, we can't do that because it's a vector. So we have to insert at func statements begin to statements end. C++, why you gotta be like that? Oh, and of course this isn't optional, so we have to dereference it, even though we know that it's already should be done. Okay, now, all right, and now we're still not printing them, we're collecting them. Okay, so let's update debug print. Where is it? Debug print. I think it's that one. Parser debug print. Oh, right, it's the function that has to do that. So function definition, debug print, name, handle, and then for statement. Oh, that's the parameter definition. That's the wrong debug print. All right, so we print that one. And we should probably print an opening bracket here. And then here, print closing bracket. And the question is, does statement, yes, statement I think prints a line. We shall see. Okay, and now you see what we have parsed is we know that we have a main function with these two parameters, and we have double foo, our first statement. So you see that it's taking shape, and we now have a data structure in memory that represents our program. But the nice thing is we already know things about it. We know that that statement, oh, I could probably have debug print look at the kind as well. Cout kind equals function call so let's just put a string, otherwise mark it with what do we say instead of call declaration. Oh, that's a good warning. Thank you, compiler. That this one is actually higher binding than the ternary operator. And now we should see, yeah, it's, you see that it's a declaration double foo. Yeah, that's basically how we do that part. So let's see if we can actually parse different kinds of statements. So this is actually perfectly valid for parsing a variable declaration statement. So we'll just copy this function, parse variable declaration, and then here say optional statement result equals I should probably have called that expect, not parse. All right, and you're happy as well. if result has value, no wait, if not result has value, so if it wasn't a variable declaration, then we should parse function call. Come on. Offer me to create it for me. Yes. Good. And basically we can add more entries like that. Return null opt should probably be in there as well. Just to be safe. Oh no, wait, return result. And now we can add more of these for other things that can be on a line. Or rather, in a statement, because those don't even have to be on lines. Okay, let's rename this one. Expect one statement. Just so we're a bit clean. And expect variable declaration. Good. So now we haven't really finished the variable declaration yet, so I guess we should do that. So if expect operator equals not dot has value, and then here if not expect operator semicolon has value, then we throw again. Semicolon at end of variable declaration. Is it actually a definition? Anyway, and so now if we have an equal sign, then with this we skip the equal sign and then we parse whatever follows it. And that reminds me, we need another kind of statement. Now my shorthand bites me. Let's just call it literal. So I guess technically they're not statements, they're, I don't know, values, operands, something like that. But you know, the terms are not important. You just need to parse it into some form. You can break it up as fine-grained or as coarse as you feel is right. And can use different data types. But the thing is, here you will need a certain basic data type, because you know, we can have in one parameter to a function, or here in the initial value for a variable declaration, we can have arbitrary expressions, which can include other function calls, which can include literals. So technically, you know, a statement can be a variable declaration or a function call, but a value can be, or it can even be a literal, technically, although that's kind of pointless. But then you have a value, which can only be used on the right side of a variable declaration or for arguments, but which can be another function call or a literal, but not a variable declaration. So, you know, there is like certain restrictions that you have to put on, and depending on what restrictions the things in your syntax tree have, you will want to depending on those restrictions, you will want to give them different names. And the C standard, like if you're actually trying to implement C, the C standard has named each of these things very precisely, and there are very subtle differences. If you just want to do any C-like language, you can come up with names that make sense to you. You know, don't let yourself be confused in writing your first programming language by you know, trying to adhere to terminology that you're still learning or something. I mean, if you can remember the terms and you find a term that exactly matches, then hey, cool. But otherwise, you know, for your own language, you can always rename stuff if you find that that term is too vague. All right, so now what we'll do is just we parse another statement here, right? So that's kind of nice. Expect one statement. And again, that's an optional statement. Whoops. I nuked half of it. Initial value, and of course if you have an equal sign you have an initial value, so if not initial value has value, something is very wrong, and you throw a runtime error and said expected initial value to right of equal sign in variable declaration or whatever. This is fine. And now we know that it has a value, so we can say statement parameters push back initial value. Oops, we want to use a value here because the star is always too subtle. Okay, so we're pushing that value if we have one. And now, of course, we need to make this parser even more smarter, and that's a technical term. So expect one statement. What else should it check? So first, we can duplicate this and say expect variable declaration. All right, so let's see. If expect, oh, we don't have an expect double yet. Well, but I think in this case we can do it by hand. If mCurrent token not mn token and mCurrent token mtype equals double literal, then result equals, wait, we need to make a double literal statement equals double literal statement type equals that would be a token type. Didn't I just add a type to statement? Literal, yeah. Statement kind literal, I guess that's what's missing. Kind literal, okay. Why are you unhappy? Oh, kind, of course, not type. That's why it didn't complete. Double literal statement name. And now we just stick current token text into it. And that way we've remembered that we have a double here. All right. I think I guess type equals, we should initialize that to void. Type void. Or actually, we can set that, but I'll initialize it anyway, because otherwise it will be unsafe. Unless we have a default constructor already. Well, never mind. Where were we? Parser. Double literal statement type equals, because actually it has the type double. Right? Okay. So, and now we can return the double literal statement here. Or rather, result equals and else we just keep trying. So this could probably also be a separate function, just like expect variable declaration. Oops, I have one too many now. Okay, expect function call doesn't really do anything yet, but should just return a null opt, right? Which is probably the same as it was before, but this one is more idiomatic. And now we need to take statements constructor here and change the debug print here and change that. So static char pointer as statement kind strings. Do the same thing as we did before, so we can easily print those types. Instead of call and decl. Kind. you unhappy? Of course, because the kind is not an integer. So first we should make sure the underlying type is integer. Does that make you happy? No, then we can typecast you as well. We could probably operate with standard underlying type here, but I'm too lazy to look up how to do that right now. Okay, let's run that again with the debugger and see what happens. So what have you parsed right now? Oh, right, we forgot. Of course, our literal parser is still slightly wrong. Here, because ++m_current token is missing. So that should work now, shouldn't it? That looks promising. Variable declaration double foo, and it has a literal double 1.5. Yes. So I should probably at least put brackets here. That it's clear what this is doing. Okay, so we have a variable declaration that is a double named foo. And I guess to make this more consistent, let's run this again. All right, so we have a double foo that contains a literal double 1.5, which has no arguments. That's just because we're reusing the data structure for everything. But in general, you see it's beginning to understand our program. It now has a separate block with like, oh, this is the value or expression that we want for a for the assignment over here. That block is now parsed separately. We have one block that says this is this assignment statement, and now we just have to cover function calls. So how do we do that? We go down to here, expect function call, and we go, again, we probably want to be able to backtrack fully, so get a start token. And now we want an identifier, optional token, possible function name equals expect identifier. And now we say if not possible function name has value, then current token equals start token, which, you know, it shouldn't have changed in that case, but again, to be consistent in case we insert something above it, that it will always clean up if it exits, and return null opt. Okay, and now we go basically do the same. Expect operator, opening bracket, parenthesis. That's what we want here. But we don't need to keep it because we know that it's a bracket. If not an opening parenthesis, then bail out again. So now we know it's a function call. And now we kind of do the same as we did up here which is we loop until we have all the arguments. Again, we need a statement, function call kind equals function call name equals possible function name text. Are we done now? Let me just bump this up a little in the hope that I won't bump into the microphone as much. All right. I hope I'm still audible here. Function call name. So, and of course we want to return the function call if it works. And now we'll say while not expect operator closing bracket as value. So we don't have a closing bracket yet. And in this case, we won't have a void. So we definitely need to have the case of just 2 brackets covered. And of course, at the end, expect operator semicolon. Should probably do that more like this. So the thing is, I'm actually making a little mistake, but I'm too lazy again to fix that now. The semicolon should probably be outside this, you know. And will probably be a little bit finicky, because like you see, for a variable declaration you need a semicolon. For a function call you need a semicolon. No, actually, no, it's right here. You know, because I was thinking Pascal for a moment. Oh God, it's been so long. Old stuff the brain drags out. So if you put a statement somewhere, there has to be a semicolon after it, you know, to make it like a full statement. So you have for example, an if statement. You have if condition, and then if you don't put curly brackets there, then you have statement semicolon else other statement semicolon. And so all the statements have semicolons after them. But that goes with those statements. Like if you put curly brackets in there, then you don't have a semicolon after the curly bracket. So it's not the if statement that supplies the semicolon, which is slightly different than in Pascal, where they actually, if you don't use curly brackets, then if you have a semicolon, so in Pascal, I'll just write it in here, just as an example, because it's cool syntax. In Pascal, you say if, you know, like foo is true, and then you say do bar, something like this. And then if you say else do buzz, I'm not 100% sure on that syntax, but it's not really important. So the thing, why aren't you? Okay, this is all a bit misaligned here because it's not valid code. So you have a semicolon here, but not here. Why is this? Well, if you decide to do nested ifs in Pascal, and you decide to not have an else statement in here, that's something in C you can't do that, because in C you have a semicolon here. So basically, in C, you cannot tell if in this code the else should belong to this if or to this f. And in fact, in C, this if will have priority and will grab this else, even though you didn't mean it to. In Pascal, they make the difference by whether there is a semicolon here or not. Because at the end of an if-then-else statement, there has to be a semicolon. So if you say if foo equals to do bar a, that means this if-then-else is finished, and there cannot be another else statement here. Whereas if you leave it away, then it's the same as in C, where this if and this else go together. And so the Pascal compiler can actually tell you if you've indented this wrong, just because there is a semicolon or there isn't. Anyway, nice aside, not really relevant here. Okay, so throw runtime error expected semicolon at end of function call. Or rather, we've written that this way previously. All right, so we have the function call, and now we have the arguments that we want to parse, and those are all statements. So of course, what we do is optional statement. We just grab each statement. Equals expect one statement that will swallow. Oh, and now we have a problem, because expect one statement expects a semicolon. But here, this is an argument list. So this is where I should have split it up, I guess, into values and statements. And then a statement would be a value and a semicolon. But I guess we can muddle around this right now. Because what we can do for now is we can say string and delimiter, and we can default that to semicolon. No, actually, let's leave away the default. And now let's see. Variable declaration doesn't really need it, because we shouldn't have a variable declaration here, but function call needs it. And of course, literal needs it. So, okay, the literal actually doesn't parse it, so we've actually already violated it here. So this is a proof that this shorthand is kind of wrong, because really we need a value that stuff without the end delimiter. So we'll just go and say we're not checking for the semicolon at the end of these, and instead only do that where we parse. Oh, did I add this after all? Yeah, we don't need this. Sorry. Thinking and talking at the same time is not always the best choice. Okay, so up there somewhere we have the code that reads a function body. Let's see. Parse function body here. If statement has value, then we check at end of statement. That should be better. And then of course we need to check for the closing bracket as well. Or rather, actually, we can go for this. While we have a semicolon, try to parse a statement. And so that statement might be empty, in which case, you know, because it might not parse anything. Or rather, no, we'll go while not has value. And now we'll do the error message. No, sorry. So this is kind of like depending on what language you're parsing, of course, this is slightly different, and C is a bit complicated in that spot. Oops. So let's see. While we have a semicolon, we try to parse something. No, that doesn't work because the start. Okay, so while true, try to parse a statement. If not semicolon, expected that one. And now if closing bracket, then break. That's also not super clean because we could enter into an endless loop here, but you know, you can work out the general programming yourself. Even this is not right because we can have the empty case. So while not expect operator curly bracket has value. So that means as soon if we hit curly open and close, then we get empty statements. Then we try to parse a statement. If it's not a closing curly, that means at the least it has to be the empty statement, which is a semicolon. And then I don't think we actually need this anymore because, yeah, we hit this up here again. So that should be correct. So now we're actually parsing multiple statements separated by semicolons. And now we need to finish parsing the function call. I'm jumping around a bit. So expect function call. We're here, but now we've fixed expect one statement, which I think I'll rename now. It's no longer a statement, it's a value. Poof. And now parameter, expect one value. So just, by the way, if I say I rename this, this is refactoring in this IDE, so it will change the name over the entire project. I'm not just typing this here. If you're a little confused about these things, I just realized that it's not obvious what magic things this IDE does. Okay, so it's not a closing bracket. Then it tries to parse a value. Then if not parameter has value, then not throw with nested, just throw runtime error expected value expected expression as parameter, something like that. I should be more consistent whether I call it parameter and argument. Okay, but otherwise we have one, so we say function call parameters push back parameter value. And so now we should be able to push a value here, and then if not expect operator comma has value, not wait, if expect operator, we had that before, if expect operator bracket has value, then we break out because we're done. A closing parenthesis, I mean, not bracket. If not expect operator comma, so otherwise we don't have a closing bracket and we don't have a comma, then something's wrong. Comma to separate parameters. All right. And I think that should be it. Now this will return a function call statement. And now, of course, we're missing one important ingredient because we have a string here. And then we have an expression here. Let's just first, let's see, I think that's 25. Let's just write it this way for a moment. I know this makes no sense as code you might actually want to run, but it still works. But because now we only need strings and integers. So we'll copy the code we already did for the double once, twice. And maybe close the split again for a moment. Integer literal. That's a literal signed integer. 32 or whatever. And maybe rename this properly. And now string literal. I think we don't have char pointer yet, so let's just I don't think we have a string type yet, do we? Let's just name it uint8. It's an array of uint8, but you know, we can always. We haven't really, so this is just dummy data at the moment, so that it will print something. String literal statement. So now we've basically the same way that we parse the double literal, where we just create a statement object, set it up with the right types, and put the text from the token, which is the number in string form, into it and mark it with the right type. That's basically what we do for all of these. And now let's see what happens if we run it, how spectacularly it blows up. Actually, it doesn't. We parsed our program. So let's compare this. You see, like, there's nothing red anymore, so that means we've consumed all tokens. That's cool. So what is it? We have a function named main, which has two arguments, which is an int and a character. Again, we don't have character arrays yet, but that's not really the point of a parser. Then we have a variable declaration for a double foo that it has the value of the double 1.5. And then we have a function call, printf. And that takes as its first argument the string, hello, it has been %d years since I learned C. And then as the second argument, the signed integer 25. And that's it. And that's the end of our function. So, yay! We parsed an entire program. Now, of course, it gets more interesting if you want to parse expressions. I think I'll save that for another chapter because, you know, I've talked long enough now. But anyway, maybe, hopefully, this has helped a little bit to at least give you a basic idea of how to recursively, like how to implement a recursive descent parser, which is what we've been talking about here. Because basically, if you look at the structure view of this class, we have all these, you know, we have the parse function, and that calls parse function body, and that calls, well, actually it calls expect function definition, and that in turn calls, you know, expect identifier and expect operator and all those low-level things, but it also then calls parse function body, which in turn calls where is the statement? Expect identifier operator, function body, expect one value. That is what it was called. Sorry. Calls expect one value to parse the individual statements, and, you know, have them separated with semicolons where needed, things like that. So yeah, we've basically done the important work, and now we have a data structure that is hierarchical. I'm not indenting that here, but I mean, we could probably just copy it over and show it with some indentation. So let's just put it in here. Oh wait, no, let's not put it in here because that will try to format it for me. Let's put it in here. Then you also kind of see it. So we have these. We have the variable, which has a literal. This we can probably just make like this. We have the function call. Which we can also shorten a bit. All right, that looks probably more readable now, and in comparison, you know, we have main, we have the arguments. In that we have a variable declaration and a function call, and in the function call we have its two arguments. So that's, you know, that's cool, that's amazing, that's progress. And now what you can basically do is, like you would go through any, you know, tree structure or graph, you could just recursively call functions on this. So like you could give our statement struct any a evaluate method, and that evaluate method would check, okay, what type am I? Am I a variable declaration? Am I a you know, like a function call, and then do something. So like a variable declaration would you know, like in a simple interpreter for a C-like language, you would just have some sort of hash map, so like standard map in C++, and just have, you know, the name foo in there, and then store the value 1.5 in there, maybe using a variant, so you can have a double or a integer or a string in there, whatever you want. Or you can even, you know, do it more complex, have like separate dictionaries depending on the variable type or something. And that way save some space or something. It's not really yeah, it doesn't really matter that much at that point. And then for printf, you know, you would just say, if, you know, the name of the function is printf, then take the first argument, print it out after inserting any other arguments in the %d sequences or something. You know, you can do all of that stuff. And that way you can build a parser that actually, or an interpreter for a language that kind of looks like C, but maybe behaves differently. So yeah, I hope that's been helpful. That is it for today. I might go back and explain expression parsing later in another video. That depends a lot on like internals of how you're going to run the code later. But you can basically build a tree structure like this that contains the expressions with correct operator precedence. So like, you know, like that multiplication is stronger binding than addition, so that 1 plus 5 plus 4 times 4 is not 6 times 4, but rather 5 times 4 plus 1. You know, that's the mathematical rules. And so that you would have to do in C, but that's not super difficult to pull off once you know the trick. Okay, see you hopefully another time. Bye-bye.